All right, so we're going to start chapter 5, okay, which is on two basic kinds of functions. First, we're going to talk about exponential functions, and then in a later section, we're going to do logarithmic functions. Okay, we'll see that these two functions are connected to each other. Okay, once we learn about logarithms, I'll show you how they connect to the exponentials. But let's just start out by looking at these two expressions. All right, so I want to look at the difference between x squared and 2 to the x. Okay, in each case, you've got a base and you have an exponent. Okay, in x squared, okay, the base is x and the exponent is 2. Okay, when I write it as 2 to the x, 2 is the base and x is the exponent. Okay, if I were to graph both of these, which one do you think would go up faster? X squared or 2 to the x? X squared? All right, let's say we plugged in, you plug in a number. What do you think's bigger, 6 squared or 2 to the 6th? This is 36. What's 2 to the 6th? 64. Okay, and this gets even more obvious as x gets bigger. Okay, pretend x is, 12. What's 12 squared? 144. Okay, we get 144. Let's do 2 to the 12th power. 2 raised to the 12th. A little bigger. All right, so what's happening here is 2 to the x grows a lot faster. Plug in a number like 20 for x, there's no comparison. This one's way, way up. Okay, so anytime you have a variable as an exponent, the function grows very fast. Okay, in fact, exponentials are one of the fastest growing functions. Okay, they curve up very sharply. Okay, and they almost look like they go straight up. Okay, so when you have a variable in the base and your exponent is a non-negative integer, okay, so no fractions, no decimals, that's a polynomial. Okay, things like x squared, 5x cubed, 9x to the 8th power. Anytime your exponent is a non-negative integer, and you have a variable in the base, that's a polynomial. Okay, everything we've studied up till now has been pretty much polynomials. But when you switch it and you put the variable as the exponent, and you can make the base anything you want except 1. Okay, so any positive number you want except 1. That's an exponential function. Why couldn't I make the base 1? What would happen if I had the expression 1 to the x? Yeah? It would always be 1. 1 times 1 times 1 times 1, it just stays 1. It doesn't matter how many times you multiply it. Okay, so if your base is 1, it doesn't grow. Okay, but your base can be any positive number you want except 1. And your exponent has to be a variable. Okay, and that's called an exponential function. So let's graph 2 to the x, okay, just so you can see what it looks like. Okay, so I'm going to graph y equals 2 to the x. Okay, I'll do zoom 6. All right. How far left and right do you think this graph is going to go? Yeah, it's going to go forever, left and right. Okay, you can see it. It's kind of hard to see on the axis, but if you graph it yourself, it does come down. So you can plug in numbers as negative as you want for the exponent. Okay, the exponent can be anything you want. As far negative or positive. Okay, the problem is, as the exponent gets bigger, okay, y starts to get pretty huge. Okay, so by the time x is 20, y is already up over 100,000. Okay, so these graphs go up very, very sharply. Okay, so your domain is negative infinity to infinity. Okay, and as a reminder, in an exponential function, the base can't be 1. Okay, we just said that. Okay, how about the range? Let's go like this. Okay, how high and low does it look like that function goes? Yep, Tommy Lee?
Greater than 0, or
Yeah.
0 to infinity.
Yeah, it's actually going to be everything greater than 0 to infinity. Yeah, it'll never reach 0. Okay, the farther and farther to the left that you go, the closer it gets. So if you try something like -5, you get 0.03. -20, we get 0.000009. Okay, so it's getting very close to 0, but it never actually reaches it. What do we call that? It's an asymptote. Okay, there's a horizontal asymptote at y equals 0 here. Okay. Okay, on the right, those are all examples of exponential functions. Okay, 10 to the x. Do you think 10 to the x would grow faster or slower than 2 to the x? Faster. Yeah, a lot faster. Okay, 4 to the v. Pi to the x, that's 3.14 to the x. That's also exponential. Okay, these are not exponential functions. X cubed. Okay, I said earlier what this was called. What's y equals x cubed? It's a cubic, but what's that big category it falls under? It's a polynomial. Okay, that's not exponential. This is also a polynomial. If you want to think of it as 1/2 x to the 4th. Okay, you just got a 1/2 in front. Same as divide by 2. Okay, the one on the right, that's a combination of a rational function, okay? But we have a square root in the top and a polynomial in the bottom. Okay, so these are all non-exponential functions. Any questions on the difference between the two? All right, so we've already graphed 2 to the x. 3 to the x would look very similar. Okay, I'll show you what that looks like. It's just going to curve up a little sharper. Okay, so it looks like it's going to stay even with it for a while, and then it curves up even sharper than 2 to the x. Any questions on those graphs? I just want you to, for now, understand the basic shape. Okay? They go forever left and right, but they don't go forever up and down. Now, what would happen if I took, let's just get rid of one of these, and put a negative in front? What would that cause it to do?
Go down.
Yeah, it's going to flip it. In this case, it's going to flip it over the x-axis. Okay, so before it kind of curved up, now it curves down. Right, so we'll see transformations work exactly the way you would expect them to. All right. Next thing I want to look at is what happens when we have a negative exponent. Okay, negative exponents make it confusing to look at our exponential function sometimes. Okay, so I just want to remind people of the rule. Anytime you get a negative exponent, okay, all you have to do is take that put it in the bottom. You flip it, and it becomes a positive exponent. So what if I had x to the negative 2?
And for 1 over s squared
How would you write that with a positive? Yeah.
over x. Or no?
This exponent stays attached to the x. It just moves to the bottom and becomes positive.
So 1 over x squared.
Yeah, it would just be 1 over x squared. What if I had y to the negative third? 1 over y to the third. Okay, so anytime you have a negative exponent, we just put it in the bottom, and it becomes positive. All right. Bless you. All right, so let's look at this. Okay, this isn't a negative number, it's a negative letter, but it's still the same idea. Okay? Think of it as negative 1 times x. Okay, think of it that way. And then if we want to rewrite it, okay, the rule for when you multiply, just write it a little bigger. If that was your exponent, the rule when you multiply is you raise a power to a power. Okay? If I was going to do this out, I would do negative 1 times x, and it would give me exactly what I have right here. All right? And now, what did I just say earlier a to the negative 1 is?
1 over 8.
Yeah, it's 1 over a. All right, so kind of the shortcut here is if you've got something with a negative letter, all you have to do is take this base and flip it. And then it makes the letter positive. Okay, so instead of a, make it 1 over a and change your letter from a negative to a positive. All right, so let's say I had, let's just say b to the negative y. Okay, if I wanted to make it a positive exponent, what do I do with the b? You just flip it. That's it. Just take your base, flip it, and it makes it positive. Right? So then I could give you something like this. Try one with a number. Let's try 2 to the negative x. How would I rewrite that?
1 over 2 over x.
Yeah, that's 1/2 to the x. Okay, and the reason we're going to want to do that is because this number tells us something very important. If it's bigger than 1, it tells us something. If it's less than 1, it tells us something else. But in order for us to use the trick I'm going to show you, the exponent can't be negative. Has to be positive. Okay? So that's where this trick is going to come up. All right, so let's graph each one of these and see what happens. Okay, somebody remind me, what was 2 to the negative x? We just did that.
1 over
1 over 2 to the x. Now, for graphing purposes, I can type it in as 2 to the negative x or 1/2 to the x. They're exactly the same thing. Okay. But I'm going to type it in the way we just rewrote it. All right, so 2 to the x, okay, which we already know what that looks like. And I'm just going to, instead of 1/2, I'm going to take 0.5, so I don't have to use my fraction bar. What do you think the difference is going to be? The blue one, we already know, kind of stays horizontal and curves up very sharply. Yep.
It curved down or no?
Yeah, this one's going to, instead of starting out at 0 and curving up, the other one is going to start up very high and curve down. Okay, so you can see these are actually mirror images of each other over the y-axis. All right. All right, so to find a complete graph, okay, all I'd ask you for here is, what was your window? Okay, and that window is fine. That was -10. Okay, so standard window is perfect. right, let's find the domain and range of each of those. Okay, let me get the graphs on one thing. All right, which one was, let's see. Okay, 2 to the x was in blue. 2 to the x, that's f of x. So this one's in blue. That one's in red. Okay, what's the domain of f of x? How far left and right does that go? Yep, negative infinity to infinity. How about g of x? What's the domain? How far left and right does the red one go? It's the same thing. It's just opposite. It's going to go right forever and left forever. All right. How about the range on the blue one? What's the lowest to highest?
You do a bracket on 0 and then 2 infinity with parentheses.
Will we actually hit 0, or is there an asymptote here?
Oh, so we do parentheses.
We do parentheses. How about on the red one?
Negative infinity to 0. Or what did you say?
So you're saying the red one goes down forever?
No, it would be the same thing.
Yeah, it goes up forever. It's the same thing as the one in blue. Okay, the one in blue is called exponential growth. Does anybody know the name for the one in red? Yeah, it's called exponential decay. Okay, at the end we'll do an example of each.
What did g of x equal?
G of x was 1/2 to the x. All right, so now I want to kind of examine this in general. Rather than using a 2 or a 3 or a 4, let's just pretend we used a. Okay, any positive real number you want. But think about the ones we just did, and that'll help you. All right, so the first one I want to look at is f of x. Okay, in our graph it was the one in blue. As x gets bigger and bigger, what happens to y? It gets bigger and bigger. Okay, for the graph in blue, okay, like 2 to the x. As x gets bigger and bigger, y gets bigger and bigger. Okay, as x approaches negative infinity, what happens to y on the left side? What does it approach? It approaches 0. Okay, on that blue graph, as you head to the left, y approaches 0. All right, now I want to look at g of x. Okay, that's where you had it flipped inside. Okay, think of it as 1/2, 1/5, 1/7. It doesn't matter what the number is. Okay, they're all going to follow the same pattern. So for the red one, what happens as x is getting bigger and bigger? Y is approaching 0. And what happens as x gets more and more negative? It's getting bigger and approaching infinity. Okay, it's going up forever. So again, this shows they're really the exact same thing. They're mirror images of each other. That's why we get this behavior that's almost a mirror image. Okay.
Wouldn't that be negative infinity?
It would be negative infinity if it did something like this. It would have to curve down. Yeah. We could put a negative in front and make it do that. But this one in red is going up, so it's positive infinity. As x gets smaller and smaller, y gets bigger and bigger. Okay, so any question on that? So what do you think decides whether a graph is going to grow or decay? Yeah? Okay, and if we get rid of that negative and just look at comparing the bases.
Oh, if it's a fraction, it's going to...
Yeah, if you get a number less than 1 here, it's going to decay. If you have a number more than 1, okay, it's going to grow. All right, so the difference we just set right here. If the base is greater than 1, we get growth. between 0 and 1, decay. And the base will never be negative. Okay, negative bases are very strange, so we're not going to talk about that. Okay. So any questions on whether you're going to, how you can tell if you're going to get growth or decay? That's all you have to look at. All right, so let's look at a transformation. Okay, and if you understand the transformations from all the previous sections, all these numbers do exactly the same thing. Okay, the stuff inside the function, that's your horizontal. The stuff outside, that's your vertical. Any negatives in front of the function would cause a flip. Any negative in front of x, that would cause a flip a different way. Okay, so if we're comparing f of x to g of x, how many transformations do we have? Yep. Okay, what numbers are you looking at for the 4?
X plus 1.
All right, the plus 1. You can start with that. And then what else? The 2 at the front.
And then the negative and 5.
This negative and 5 is all together.
Oh.
Okay, the only time you have a negative that does something separate, if it's on the x or on the 2. All right, so this negative we'll talk about in a second. So there's only three transformations here. Okay, who can tell me the first transformation? And make sure we do it in the right order. Yep.
-1.
All right, just explain to me what's the transformation. Yep. Yeah, shift left 1. Okay, so make sure you say which direction and how much. Left 1. Don't write shift left -1. That's confusing. Either shift left 1 or shift right 1. Okay, in this case, shift left 1. This takes care of it being negative, saying left. All right. Second step. Yep.
Horizontal stretch by factor 3.
So to have a horizontal stretch, we'd have to have a number next to x, like that. Do we have a number next to x in this one?
It's just 1.
Yeah, it's just 1. So there's no horizontal stretch in this problem. Mm-hmm.
Would it just stretch by 2?
Yeah, we have a vertical stretch by a factor of 2. And what about that -5? That's going to shift down 5. All right, so I'll give you an example with everything in it. If you had something like -4 times 3 to the -2x plus 1 plus 6. Okay, this is your horizontal shift. This would be your horizontal. Is this going to stretch or compress? Compress. Compress by a factor of 2. This is your reflection. Okay, in this case, reflecting over the y-axis. This 4 is your vertical stretch. This is another reflection, in this case over the x-axis. And the plus 6, that's a shift up 6. Okay, so that example has everything in it. Most likely on a test, I'm going to give you one that's got like 3 things in it. Not all 6 things. Okay, questions on that? Okay, and it's just a reminder, that's your order. Okay, and it's exactly the same order in the problem I just did as it was for this, as it is for every function we study all year. Okay, any questions on how we got those? Yeah.
So the only difference in last night's homework is that the horizontal stuff comes out of the exponent instead of the base.
Yeah, the horizontal stuff now, is always the stuff that's inside, whether it's inside parentheses, whether it's inside a square root. Okay, it's all horizontal is always the stuff that's inside. Vertical is always the stuff that's farthest away. It's outside. Yep. No difference in how you describe the transformations. All right, this one, I just want you to watch me graph it, okay, because we get something kind of interesting here. Okay, it's just kind of a weird graph to imagine what it's going to look like. Because you have 1 divided by x. What happens if you take 1 and divide by a huge number? What do you get? Something what? Yeah, very close to 0. So if I take, like, let x be 1,000,000. 1 divided by 1,000,000 is very, 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 very small. And then I'm going to add 1. So I get a number extremely close to 1. But then I'm going to raise it to a huge power, like 1,000,000. So I want to see what happens when we do that. Okay, and something kind of interesting happens. All right, so 1 plus 1 over x raised to the x. Well, first of all, we get a vertical asymptote at 0, because you can't divide by 0. So it's not a connected graph. But what does it look like is happening here? We have a name for this. Yeah, we're getting a horizontal asymptote. And if I let x get really big, we'll start to see where it is. If I let x be 10, get about 2.6. If I let it be 500, we get about 2.71. If I do that, I get 2.7181. Okay, so notice it's getting pretty close to this 2.7 number. If I go the other way, we're getting the same thing. We're getting this negative 2.7 number. Has anyone ever seen that number, 2.7? It's actually a special number, okay, like pi. Okay, pi stands for 3.14. Well, this is a number called e. 2.718281828. It doesn't keep repeating 1828. I don't know what the next number is, but it's not a 1. Okay, so that number is e. It's a horizontal asymptote. And for now, the only thing I'm going to say about it is it's going to be our base when we do natural logarithms. Okay, so if you've ever seen the button ln on your calculator, and you wondered what ln stands for, it stands for natural logarithm. Okay, and when we look at that later in chapter 5, this number e is going to pop up. Right, so it's just kind of weird that we get this horizontal asymptote right at e if you graph that function. Okay, but that's all I wanted you to see. Hey, if you're not familiar with natural logarithms yet, that's fine. Don't worry, we're going to study logarithms later on. Okay, but since we're studying functions where we have variables as exponents, this is a good time to show you this type of function. Does everybody have that number down? E? All right, so last thing we're going to do is look at a few different types of word problems. Basically where we have exponential growth, maybe of a population, or like a bacteria. Might have studied that in like science. A bacteria doubles every hour. How much will I have in a day? Okay, kind of thing. All right. And this is your formula for exponential growth. Okay. I'm going to do it with a population, but population could be anything. Could be an amount of bacteria, could be a number of items. Okay?
Is that 1 plus 5 or 1 plus r?
So that says p times 1 plus r raised to the t. Okay, and we got to know what each variable stands for. Okay, p in our problem is going to be the initial population of a town. But again, it doesn't just have to be people. It could be any initial amount of stuff. Okay, R is the rate at which it's increasing. So they might say the population of this town is growing at 2% every year. And T, that's our time. Time is usually going to be measured in years. Right? If they give you a growth rate in years, then time is measured in years. Okay? And it's important that whatever rate they give you, you make it a decimal. So for example, what's 12% as a decimal? 0.12. Okay, if you had something like 3%, it's 0.03. Okay, so make sure you change your percent to a decimal. Okay, but that's the exponential growth formula. And it turns out to get exponential decay, you just have to change one thing in the formula.
1 minute off.
It's going to be 1 minus r. Okay, all the letters stand for the same things. All right, so if you said it had something like we had 50,000 acres of forest, and each year they cut down 2%, how many acres will be left after 5 years?
1 minute.
That's a decay problem. And if they keep cutting down the same percent of trees every year, it's an exponential decay, meaning it's going to drop very quickly. Okay? Right, so let's look at an example. Right, so we have a town that has an initial population of 50,000 people. It's growing at a rate of 2.5% per year. Okay, first thing I want to do is write a formula that'll model this. So let's find our population as a function of time. Right. Since it's changing at a constant percent, that's exponential growth. If it said 500 new people move to the town every year, that's not exponential growth. That's just plus 500 every year. This is a percent increase. That's exponential. Okay, what's the first thing I have to have in my formula? 50,000. Okay, that's my initial amount. Times 1 plus,
0.425.
what's my rate here is 0.025. And last thing I need,
2.5. 1.
time. Exponent of t. Okay, if you can combine anything, just add those up. So it's 50,000. What's 1 plus 0.025? 1.025 to the t. There's your formula that gives you your population as a function of time. And now the question is, I want to know when this population hits 100,000. So where would you plug that in? Would you plug that in for t? Or would that be p of t? Yeah, that's your population. Right, so how could I do this on the graphing calculator?
Maybe
Y is
y technically.
So yep,
have one Y as a problem at the end, and the second line is like 100,000.
yeah, let's type our formula into y1. 50,000. 1.025. Okay, we have to use x. And put the population you want to hit at 100,000. Now, typing this in correctly does nothing if you don't have the right window. Okay, so what would make sense for an x min?
0.
Yeah, we're not going back in time. X max is how many years we're going to go ahead. I don't know, let's set it to 40 years and see if we hit it. If we don't, we'll go a little bigger. How about y min?
0.
Yeah, we're never going to go lower than 50,000. Okay, the population can't drop below that. And how high should I go?
100,000.
Yeah, just go a little above 100,000 so it's not on the edge of the screen. Okay, there's your population. It's hard to see, but it is curved. There's 100,000. And now what do I do? I just find where they intersect. Okay, so it's going to take about 28.07 years. Assuming that the population continues to increase exactly the same every year.
Would you put for time calculators put X?
For time, you use X. Yep.
Just as a component?
Yep. Put that. Okay, so you type it in just like that. Do your graph, get your intersect, and then just write down your time. Okay. Any questions on that one? All right, let's look at another example of exponential growth. It has to do with the bacteria doubling. As always, okay, you guys already did this in the last problem. Just be careful about your mins and maxes. Use common sense with time and things like that. Right? Right. Let's assume that in this one we start with 100 bacteria and it doubles every hour. It doubles every hour. So at the very beginning, we'll call that time 0. We have 100. Okay. How many bacteria would we have after an hour? We'd have 200, which I'm going to write like this. Think of it as 100 times 2. 200. Okay. How many bacteria after 2 hours?
400.
400, which I want you to think of it as 100 times 2 to the second. How about after 3 hours?
800.
800. Again, I want you to think of that as 100. 2 cubed is 8. It's 100 times 8. Notice the exponent, and notice the hour. So how about after t hours? What do you think the formula would be?
100 over
100 times what?
100 times
2 to the t. It's basically the same as what we just had. We have an initial amount times a number raised to a variable. Okay, so this is the formula for something doubling. Okay, initial amount times 2 to the t divided by the length of time to double. Okay, if something is doubling every hour, then the length of time to double is 1. Okay, so a lot of times this is a 1. Okay, it's very similar to the last problem. Okay, this one says, suppose you have 100 bacteria. It doubles every hour. I want to know how long before I hit 350,000 bacteria. Okay, so we'll find our amount of bacteria as a function of time. Okay, what's my formula going to be for this one?
100.
Yep, start with your initial amount times what? Well, Tyler? So what's going to be my formula for the amount of bacteria here as a function of time? So we've got our initial amount. And what comes after initial amount? Yep, it's going to be exponential growth. Yep. So what comes after the initial amount? Two, right? 2. And then what's our exponent? 2 to the time, t. That's it. So our amount, just the initial amount. Okay, we're starting with 100. Then you put a 2, because that's what's in the formula. And your exponent is t. And this problem says it's going to double every 1 hour. Okay, so the length of time to double here is just 1. Okay, if it said the bacteria doubles every 3 hours, then I would have put in a divide by 3. Okay, if it said it doubled every 6 hours, I would have put a divide by 6. If you want to put divide by 1, you can. But you don't need it. Right? And then now how would I solve this problem? How do I figure out when it hits 350,000? Yeah, what would you type in?
Problem for the first 5. Because this other one would be 35 and 350,000.
Yeah, so
Same
type.
thing we did last problem.
Same thing we did last problem. Put that in y2. Put that in y1. Calc. And then intersect. So I'll leave that part for you. Okay. Same exact thing we did on the last one. All right, let's take a look at our last problem. Okay, it's exactly the same type. The only difference is instead of something growing, it's decaying. Okay, has anybody ever heard of that before in science? Half-life of something?
Yeah. It's like when it's like anticipated lifespan, like already happened.
Yeah, so if I heard somebody say radioactive.
Radioactive elements.
Yeah, that's one thing you could use it for. So for example, the half-life basically means if, say this thing I'm holding is radioactive, the half-life is the amount of time for half of it to disappear, to break down. All right? And then after another half-life, half of what's left is now gone. Okay? After another half-life, half of that's gone. Okay, so if you start with 100 grams of something and say it had a half-life of an hour, after an hour you'd be down to 50. After another hour you'd be down to 25. After another hour, 12.5. Okay? And the problem with radioactive things, sometimes they have half-lives of thousands of years. So if you start with tons and tons of radioactive waste, it might take thousands of years for half of it to break down and become safe, right? And then another 1,000 years for half of what's left. Okay, so this kind of stuff sticks around for a long time. On the other hand, some things have half-lives of milliseconds. So like like experimental stuff. So the second you create it, it's only around for like milliseconds and then it's gone. So it's very hard to study those kinds of substances. Yeah, did you have a question?
It never actually disappears and gets smaller and smaller.
Really, yeah, it never actually disappears. It's same idea when you take like medication. Usually if you take like Advil or different kinds of medication, there's a half-life to it. So after maybe 6 hours, half of the medication you took is gone. Another 6 hours, half of that's gone. So it's really never completely gone. It's just smaller and smaller and smaller and smaller. Eventually it's so small it basically doesn't make a difference. But you're right. It's kind of like that problem, walk halfway to the wall. Has anyone ever heard that? Like walk halfway and then walk halfway again and then halfway and halfway. You never reach the wall if you just keep walking halfway to it all the time. You get closer and closer and closer. But in reality, you can't really do that because we can only step so small. But theoretically, you never reach the wall.
So it's like an asymptote?
Yeah, it's like an asymptote. Yep. So when your substance decays, it approaches zero, but it never actually reaches it. But at some point, it's so small, who cares? It doesn't matter anymore. It's very small. Okay, so this one, same basic formula. It's initial amount, except instead of doubling, now we're halving. So just change the 2 to a 1/2 and everything else is the same. All right, so we're going to find an equation that models this, and then figure out when we'd have less than a gram left. Okay, so my amount as a function of time. Take the initial amount. Okay, I'm starting out with 5 grams times a 1/2 to the t. And what's the length of the time for it to cut itself in half here? Half-life is 20 days. Okay. Now the second part, I want to know when I have less than 1 gram. I'm going to type 5 times 1/2 to the t over 20. Put that in y1. Just to make it easier, I'm going to use 0.5. X over 20. I'm going to put a line in at 1. And for my window, okay, we're never going to have more than 5 grams. I know it can never be less than 0. Okay, it's just going to get smaller and smaller. And let's graph that and see how it looks. So there's my substance going down. Okay, so 40, it's not going to happen within 40 days. Let's go out to 75 days. Is that going to be less than 1? Yeah. Okay, so there's my substance decreasing. And on the 46th day, that's when I'll have 1 gram. So any time after that, I'll have less than a gram. Okay? It's just gonna keep decreasing after that point. So 46.4 days. Okay, does everyone see that any time after 46 days, you just have less and less and less? It just keeps dropping. Question on that? Yeah?
So the 20 I think is the actual half-life, right?
Yep. T is the exponent, length of half-life is 20. All right, so homework tonight. Okay, it's on 268. Okay, I'd like you to try 4 through 7, 19, 25, 27, 31, 35, 47 to 49, and 57.